In this video, we're going to look at what a cross product is, how to find it, and then how to use it to find the area of a parallelogram. This is going to be a little bit more of an involved process than, say, dot product or magnitude or something like that. And what we're looking for is this right here, this U crossed with V. So if I have U and V and they share a terminal point, I'm looking for the normal vector, the vector that is perpendicular to both of those. So this is a pretty good example. And imagine you got a piece of paper that's laying flat, and you go to one corner and you stab it with a pencil. That pencil is your normal vector. That guy that's shooting straight up like this. So it's going to be a 90-degree angle to both sides, or also a corner, right? If you're thinking about a room that where those two walls meet, it's going to be that seam in that corner there. And we're going to look at, well, what is the coordinates of that vector? How, where is it going? Even though we know it's 90 degrees to both of these, that doesn't mean that it's, in reference to maybe the origin opening at a 90-degree angle, right? So this could be turned in any which direction. We're going to use determinants to help us out, but we're not going to be able to use our calculator because it is going to have our first row is going to be I, J, and K. And so let's see, I'm going to scoot back. We know a couple of things about how to find a cross product. It's not really too bad. And we're going to do something that looks like this, even though this looks pretty bad. You're basically finding a 3x3 determinant. But the problem is that my first row is not going to be a number to where I could just go ahead and multiply it or add and subtract and be done. I can't use any of my cheats that I had for 3x3 determinants in other classes, like my calculator or my little diagonal trick. We're going to need to do this the old school way. And so if I wanted to find V crossed with W, now it does matter who comes first for direction, right? So V crossed with W would just be upside down if we were looking at it the other way, but it's a different direction. So you would have the same absolute values for your coordinates, but it would be going the wrong way. So V crossed with W means V goes in line 2 and W goes in line 3. And so we're going to be looking at something that comes out like this, but let's look at how this actually is going to work. So I'm going to come over to the other side and write this out. So in my first row, I'm going to have I, J, and K. V is going in my second row, 3, 5, -2. And W in the last, -2, -2, 1. -2, -2, 1. Now, you can use the formula. The formula looks a little crazy. You can use the diagonal trick. I like to use the trick where you cross out your first row and then you cross out your first column. And the piece where they overlap, that is your scalar. And the piece that's left in here that isn't crossed out, you're going to find the 2x2 determinant left inside of there. And then you're just going to repeat that 2 more times. So now I'm going to take this piece and do my next one. Scoot that over. That's my scalar. I know I'm writing it backwards, but that's because it's a variable. And the 4 pieces that are left, that makes my little 2x2. Now, the second value, whatever you get in this one, is going to be negated. It's keep, negate, keep, negate. If let's say you had 4 or 5. So we're going to go keep, negate, keep. So this one is going to be a keep. And when I say keep, I mean keep the sign that you get out of this determinant. It's not, don't think positive, negative, positive. That's not true. It's keep the sign, negate the sign, keep the sign. The last section, I scoot that over, K gets crossed out. So K hat is my scalar, and then I have this little determinant that I need to find, 3, 5, -2, -2. And it's easy to find a 2x2 determinant. It's kind of like a little crossover, right? So it would be 5 minus a 4, which is a 1, and I hat. Minus, I got my j hat. This is going to be 3 minus a 4, and that is a negative 1, so that will wind up getting negated. And then my last one is 6 minus a negative 10. I keep the sign on this. Its scalar is k hat, and that's going to be a positive 16. And so my cross product is I hat plus j hat plus 16k hat. And you can write it in vector form, or you can write it in component form. Really doesn't matter to me. Whatever you want to do is fine. So if I had these two vectors, which are not going to look nice if I try to draw them, right? You got something that looks like this. One of these is V, one of these is W. The guy that's shooting up, straight up, so that I'm going 90 this way and 90 this way, is going to the point 1, 1, 16. So it's not perfect up and down. He's kind of like twisted a little bit, but I can't really draw 3D on a 2D plane. That's it. That's all you have to do. It looks very fancy, but that's really all there is to it. So there's a couple of them right here. V by W, that's what it looks like. And you get out negative 17i minus 18j hat plus 10k hat. If you do it upside down, you get an upside down normal vector, right? So if you find one and then you just flip them, they're not commutative. They negate with the commute, right? So they go in two different ways. One's pointing up and one's pointing down. And sometimes you want things that are pointing down. It really kind of depends on what it is that are you looking at solar panel coming in, or are you looking at energy going out? One's up, one's down. Now, when you cross something with itself, you get nothing. You can't cross with yourself because you cannot make a 90-degree angle with something that is going the same way as you, right? So this is kind of like having a linear system where the two lines were the same and they're on top of each other, right? Something like that. Or maybe I should say, well, yeah, it's more like that than the parallel. They're the same. You can't get an angle between them if they're the same. Same thing with W and W. So what do you do with a cross product? Actually, you can do some pretty cool stuff with a cross product because it's a normal vector, and sometimes we look at another project that has to do with using normal vectors for shading. Like I said in a post, I'm sure at some point, that gets pretty crazy pretty quickly. So I don't always do it, but I find it pretty interesting if you ever wanted to look at that. One is like Fong shading. There's like something with a G, garage, some shading, uses normal vectors. It's very cool stuff. The other thing that we could do with it is find out if two vectors are indeed orthogonal. These are important things to check. You may want something to be specifically orthogonal. Like your walls and your floor, you want those things to be at a perfect 90-degree angle. So if something is orthogonal and you find the dot product, the cross product between them, you can then use that to see if the dot product is going to be a 0. So is the dot of these two vectors a 0? Yes. All right, then that is orthogonal, right? So remember that from what, with your cosine, finding the angle between the two. The other thing, much more interesting, is finding the area of the parallelogram. You can kind of think of the normal vector of kind of casting a shadow diagonally. Right? We'll say something, let me go back to that picture. Something like that. And so this pull, if you will, it's saying, well, how far out are we going to stop this? Like, where are we going to go with this angle? Do they really go on forever? What's its effect size? Let's talk about it like that. What you'll have to do is go through the process of finding the cross product. That's the long part. But then you're going to just go ahead and find the magnitude of that vector. This is the formula behind it. It's a lot easier to actually do. So we're going to go in a little bit of a strange order, I think anyway. So you have this parallelogram, and they don't label it the way that you would think. They don't go P1, P2, P3. They put P3 down here. It's very strange that they don't do it the right way in the, for the, like it's a geometric shape, but they don't label it circling around like a geometric shape. So you're going to look at this one, P1 to P2, and P1 to P3. In our textbook, that's always the way it goes. Could you look at other ones? Sure. But when you got a 0, 0, 0, that makes life pretty easy because you're going to be able to find the position vector pretty quickly. So once you have these two, you cross them. That's a little bit involved, but it's not terrible. Find the magnitude of the cross, and that is going to be the area of your parallelogram. That is it. Unfortunately, there's no cheat in the calculator. You really got to like bust it out and do it by hand. But it's not so bad, and it's a little fun. And that's how you use a cross product to find the area of a parallelogram.